Alright, so here we are in Chapter 4, Applications of Differentiation. We're going to be talking about Section 2 in this video. The PowerPoint slides that I'm using are from Stewart's calculus book, Early Transcendentals, 8th edition. In this video, I'm going to go through these provided slides. Some of them I'm going to use, some of them I am not. And then after talking through these slides and making some additional notes on them, I will work out a few example problems. So when talking about the mean value theorem, the first thing that we're seeing on this slide is Rolle's theorem. And Rolle's theorem has these three hypotheses that are part of it. One is that the function that we're working on has to be continuous on a closed interval, and a closed interval is indicated by these square brackets that are here, so we're including our a and b values there. The function has to be differentiable on the open interval, so we're seeing parentheses there, excluding the values of a and b, and the y value when x equals a must equal the y value when x is equal to b. So the y values at the end points of the interval must be the same. If those three conditions are met, then we know that there is an x value, c, in the open interval such that the first derivative evaluated at c is equal to 0. In other words, the slope of the tangent line somewhere on that interval will be 0. In other words, there will be a horizontal tangent line somewhere on that interval. Here are some examples. Now at the top of these slides it says the mean value theorem, but be mindful, at the moment we're talking about Rolle's theorem, which is all about horizontal tangent lines or tangent lines that have a slope of 0. Notice that at the beginning of this interval and at the end of this interval, these points have different x-coordinates but have the same y-coordinate, which means that the line drawn from one to the other has a slope of 0. The slope of the tangent line at this point, strange to think of a horizontal line or a line at all having a tangent line, but another way that you could think of it is the first derivative, or the slope of the function at this point, is 0. And the slope of the function, the rate of change of the function, dy over dx at that point is also 0. And the slope of the line connecting our beginning point to our ending point is also 0. So going from here to here, if we drew a line from one point to the other, the slope of that line would be 0. And that's the blue line that was given to us. Another example. Notice, from beginning to end, if we draw a line, the slope of that line is 0. It's a continuous function between those 2 points, it's differentiable between those 2 points, and sure enough, there is a point with an x-coordinate between a and b such that the slope of the tangent line is 0. And that holds true for these other two examples also. In example C, we're seeing 2 points, actually, that have a horizontal tangent line, or where f prime is equal to 0 on that interval, and in part D there's only one c value on the interval that satisfies Rolle's theorem. In each case, it appears that there's at least one point. That's true, at least one or more. Thus, Rolle's theorem is plausible. Now, I put a little mark in the top left corner of this slide because I don't want to talk about this one. I'm going to leave it up here for a moment. You could pause it, you could look at it, but I don't want to spend time talking about that one. We're going to see some example problems, remember, after we march through these slides. This is pertaining to the previous slide. This is pertaining to the previous slide. It's not a bad example problem. I just don't want to spend time talking about it here. All right, now Remember, these slides are titled, they're all titled the mean value theorem, but now we're actually going to talk about the mean value theorem. which is what? This also has hypotheses. There are only two. So f is a function that satisfies the following hypotheses. It has to be continuous on the closed interval, and it has to be differentiable on the open interval. If those two are satisfied, then there is a number c on the interval, so somewhere between the beginning and ending point. There's an x-coordinate such that the first derivative evaluated at that x value will equal, and what's this? This is the slope of the line between the beginning and ending point. On the next slide, it's going to be the blue line. So in figure 3 and in figure 4, the blue line connects the beginning and ending points of those curves on that interval, and the slope of that blue line is calculated by essentially doing y2 minus y1 divided by x2 minus x1. Slope. Perfect. Or equivalently, if we multiply both sides of that equation by the denominator, b minus a, then we get this second equation that's shown to us here. So we can use those interchangeably. The mean value theorem is a more generalized version of Rolle's theorem. Rolle's theorem, remember, required that the y-coordinate of the beginning and ending point be the same, which means that the slope, for sure, right, y2 minus y1, was always going to be 0. The mean value theorem is more generalized than that because there's no restriction on the y values of the beginning and ending point. So the slope won't always be 0. It could be something else, but as long as f is continuous on the closed interval and differentiable on the open interval, then we will be able to find a point between the beginning and ending point such that the slope of the tangent line at that point will equal the slope of the line that connects the beginning and ending point. Look at those two lines that I circled. They're parallel because they have the same slope. Here, there are actually more than one point. There is actually more than one point that has a tangent line where the slope of that tangent line is the same as the slope of the line that connects the beginning and ending point of the interval. That's the mean value theorem. So the slope of the secant line from A to B is the slope of the line between A and B is y2 minus y1 over x2 minus x1. Great, we've known that for years. Since the slope of the tangent line is, well, I should say, since the first derivative evaluated at C is the slope of the tangent line at that point, C comma f of C, the mean value theorem in the form given by equation 1 says that there is at least one point such that the slope of the tangent line is the same as the slope of the secant line. In other words, the slope of the secant line, that was represented on the previous slide as lowercase m with a subscript of ab, and I circled it as being the slope of the line that passes through the beginning and ending point. So this slide is saying, has written out what I said verbally when we were looking at the previous slide. Here we're illustrating the mean value theorem with a specific function. So we've got a third degree polynomial, x to the third minus x. Here's the interval, it's going from 0 to 2. This function's a polynomial, which guarantees that it's going to be continuous and differentiable, not just on the interval, but for all x values. That's nice. So we've satisfied the two conditions of the mean value theorem, which means that there is a number c on that interval such that, and here they're using the second version of that equation. We could modify this. We could take the 2 minus 1 and divide it back over underneath here. Sorry, 2 minus 0, so that we have, again, y2 minus y1 over x2 minus x1. But your author is choosing to use the modified version here. So what's happening on this slide is we're finding the y coordinate at the right-hand end of the interval when x is equal to 2, and we're finding the y coordinate at the left-hand end of our interval when x is equal to 0, which means that the slope between those 2 points is going to be 6 minus 0 over 2 minus 0, so that's going to be a slope of 3. Pardon my equal sign there. And we're also going to take the first derivative of the given function, so that ends up being 3x squared minus 1. And when we substitute these values into this equation, y2 minus y1 is 6. So down here, the left-hand side of the equation says 6. And the first derivative on the upper slide, the first derivative, f prime of c, is 3c squared minus 1. We don't know what c is yet, but we're looking for a specific value, so that's why we've put c in there instead of an x. And then the 2 minus 0, obviously, is where this 2 is coming from. And then we have to solve this equation for c. And when we do, we have to take the square root of 4/3, which gives us a plus or minus 2 over root 3. But the c value that we're looking for is supposed to be in this interval from 0 to 2, so a negative c value doesn't make any sense. So it must be that the c value we're looking for is 2 over rad 3. We know how to rationalize denominators. That's not the focus of the process here, so your author has not rationalized the denominator. But realize that if it's a multiple choice scenario, or your professor specifically might require that. So be careful there. And here's a graphical depiction of what we've just been working on algebraically. We can see in black is the actual curve, and in blue is what we're calling the secant line, going from our beginning point of 0, 0 to our ending point of 2, 6. And here is our x-coordinate c that puts us at a point on our curve where the tangent line is parallel to the secant line. Kind of cool that that is always going to happen at least once on that closed interval. The format of example 5 is a little bit different. Here we're being told that 0, -3 is a point on our function. We don't know what the function is. And we're being told that the first derivative, or the slope, of our function, the rate of change of our function, is less than or equal to 5 for all values of x. So never is our curve or our graph going to be sloping upward too rapidly or really, really fast. The slope of the tangent lines are all going to be less than or equal to 5. And then the question is, how large can f of 2 possibly be? Well, if I were working on this problem, well, let's go through and look at it how your author presents it, and then we can talk about maybe a different perspective. So your author's solution says that we're given that f is differentiable, so we're good, which means, especially because if it's differentiable, then that means it's continuous everywhere, so we're covered on the interval that goes from 0 to 2. We can apply the mean value theorem, therefore, on that interval, which means that we're going to find a c value that satisfies this statement. And again, we could divide both sides of that equation by 2 minus 0 in order to have y2 minus y1 over x2 minus x1 if it's more convenient or familiar for you to be working with the equation that way. But we go along to look at the y value when our function is equal to 2, right? So where is this coming from? Well, on the previous slide, we see f of 2, so that's a y value. F of 2 minus f of 0, those are on the left-hand side. It looks like this has been added to both sides of the equation so that it's appearing over here somewhere. And in fact, yep, down here, there's the f of 0. Okay, and then we've got this value of 2 right here is coming from the 2 minus 0. And then f of c in this upper equation is present right here. Okay, so all of those components are matching up. We can see where those different pieces came from. Oops, sorry, I just wanted to clear out some of my circling. Right, all right, so this is where we were. And when we sort of clean things up on the right-hand side of this statement, we're seeing a -3. Where does that -3 come from? It looks like it's matching up with f of 0. On the previous slide, f of 0 is equal to -3. Okay, so that makes sense. I'm just making sure that I know where all these different things are coming from, and when you go through and read somebody else's solution process, you're going to need to do some investigation like this also. Alright, so let's stay focused on this. F of 2 equals -3 plus 2 times f prime of c. I'm seeing those same components down here, and we were told that this quantity, I suppose you could say, needs to be less than or equal to -3 plus 10. Why is that going to be less than or equal to -3 plus 10? I'm seeing a -3 here. I'm seeing a -3 here. All right, those kind of match up. And then I could even match up the plus sign with this plus sign. But how does 2 times f prime of c, how does that sort of become a 10? We have to go back to the previous, oh no, they wrote it for us here. The first derivative at c needs to be less than or equal to 5, and if we multiply both sides of that little inequality by 2, we get this statement. And then, looking at this statement right here, if we, it's a little unusual to do it this way, but if we add -3 to both sides of that statement, then a -3 will appear right here, and a -3 will appear right here, and you will have this statement right here. It's strange to be putting these values back into an inequality like this. It's more familiar to most of us to, give me a different color here. It's more familiar for most of us to start with a statement that looks like this and then simplify it by adding 3 to both sides in order to end up with a statement that looks like this, and then divide both sides by 2 and end up with this. So here we're sort of reverse engineering the thing that we need, the statement, the comparison that we need. And since the left-hand side, I'll keep my giant blue pen here, since the left-hand side of this statement is f of 2, and the right-hand side of our statement is, notice the equal sign right here, the right-hand side of our statement is equal to the positive 7, we get to say that f of 2 is 7. We've been talking about this problem for so long, I don't even know what it is that we're solving anymore. Let's go back to the beginning. What are we trying to find here? Suppose that f of 0 is equal to -3 and f prime, 5, all x. How large can f of 2 possibly be? So if we're typing in an answer or handwriting it or choosing it from multiple choice, the answer is 7. Wow, that was a lot to go through for an answer of 7. And then we go on to talk about another theorem and a corollary on the next slide. What I'd like to do is back up to the original question. When I'm solving problems on my own, or when I'm in the classroom and solving problems, I tend to do things a little bit differently sometimes, as a lot of professors and instructors do. And one of the things that I really like to do is I like to draw a picture. Sometimes it's helpful. So when I'm looking at, let me do a little erasing real quick. What I'm doing, if I were doing this problem on my own, I might look at this problem and say, well, here's 0, -3. I'm going to need to be plotting that point. And I want my slope to be less than or equal to 5, okay, which means that I'm working with maybe an increasing function. I suppose it could be a decreasing function. It's not going to be a function that curves up like this, because here my slope is much greater than 5, right? That's too steep. Okay, so I'm going to get rid of that. And I'm going to end up somewhere over here at f of 2. And I'm working with slope. So I'm at 0, -3, which is here. 1, 2, 3, -3. And I'm coming over to an x-coordinate of 2. And my slope has to be less than or equal to 5. Well, how could I make it equal to 5? Well, that's just rise over run. Slope is rise over run, so this is like 5 over 1. 5 is the rise, 1 is the run. But as I go from a point that has an x-coordinate of 0 to a point that's going to have an x-coordinate of 2, I'm running a total of 2. So 5 over 1 is equivalent to rising 10 and running 2. So let's start over here at our point that has the x-coordinate of -3, and let's rise 10. 1, 2, 3, 4, 5, 6, 7. All right, so total, I've gone up 10. And now I need to run 2. And I end up at this point. And what are the coordinates of that point? 2, 7. I'm looking at the question again. How large can f of 2 possibly be? Well, if I'm going to keep my slope less than 5, I would say my y value can't be any larger than 7. If it were, my point would be up here, and the slope between these 2 points would be greater than 5. I'm trying to avoid that, so I'm going to max my y value at 7. It's more conceptual, maybe. It's more visual, for sure. Maybe it's less conceptual because it's actually visual. If I have the opportunity to draw a picture of a scenario, that's the route that I typically take. Whichever one of those two processes works for you the best, that's the process you should use. Unless your professor is requesting a specific process, then maybe you can use your process just to check your work. All right, on this slide, we see an additional theorem which says that if the derivative of a function is equal to 0 for all x values in an interval from a to b, then the function is constant. Yeah, I think that's reasonable. If your slope is equal to 0 everywhere, then it's a horizontal line, which means your y values are changing or not changing. Not changing. What's a synonym for not changing? Constant. Great. Number 7, as a corollary, if your first derivatives of two different functions are equal to each other, then the slope or the rate of change for both of those functions is the same everywhere. They're increasing or decreasing or neither at every x value. They're kind of matching up. for all x values on an interval, then the difference between the functions is going to be constant. In other words, there's only going to be a c value of a difference between them. Is there a depiction of that? There is not. Let me see if I can just sketch one real quick. You could do this even with like a couple of parabolas or just portions of parabolas. So if I can draw this one, and then really what I should be doing is copy and pasting and creating, oof, terrible. Back up, back up. What I want to draw is exactly the same shape, essentially just slid down a bit from the red one. The slope of the tangent line here is the same as the slope of the tangent line here. Let's pick another x coordinate. How about this one? The slope of the tangent line here is the same as the slope of the tangent line here. So that's what the corollary is telling us. So if that's true, if the slopes of all of those tangent lines at any one of those particular x values is the same as we march our way across the curve, or whatever the graph is, then essentially the two functions are the same. The only difference is that they've been translated or vertically shifted up or down. That's the only difference between them. All right, interesting corollary. And then our last slide pertaining to the mean value theorem says that there are some unusual functions out there, and you need to watch out for them because your knowledge of the details of the hypotheses that are parts of corollaries or theorems might really be tested. So giving this slide a quick read wouldn't hurt you to see an example of one of the sort of contradictions that you might have to watch out for. All right, that is the end of those slides. Let's switch over, see if I can do this gracefully today. Nope, failed again. I don't know why it is, when I'm screen recording, I can't access my other apps. Well, I did want to have photos available because I want to access this photo, and I also wanted my notepad. All right, let me write down very quickly a function for us to work with. Right, so I've called this problem number 5 because in the homework set that I'm going to be assigning to my own students, this is problem number 5 from their homework. It's an adaptive software, so they're going to be seeing their questions asked with some different values, maybe on some different intervals, but this is still good practice for all of us, and we're trying to find all the c values that satisfy Rolle's theorem. We also need to make sure that the conditions are in place for us to be using Rolle's theorem at all. So let me grab a different colored pen and let's make sure that we're satisfying the conditions of Rolle's theorem. The first thing we have to make sure is that the slope of the line that connects the beginning and end points of the interval is 0. So let me tear through some arithmetic for us real quick. All right, so these are the x coordinates of our beginning and ending point of our interval, and these are the y coordinates. So we actually have, let me come back over here to the right hand side, this is 2, -15 are the coordinates of our beginning point, and 4, -15 are the coordinates of our ending point. And what that means is that the slope between those 2 points is 0. Great, so we're happy about the fact that the conditions are in place to satisfy Rolle's theorem. Actually, the other conditions that we have not addressed are the fact that the given function is a polynomial, and since it's a polynomial, it implies continuity everywhere, and so definitely on the closed interval from 2 to 4. Polynomials are also differentiable everywhere. So again, since it's a polynomial, it's going to be differentiable on the open interval from 2 to 4. Parenthesis, there we go. And as was stated in the slides, the comparison was that f of a needed to be equal to f of b, and in this case it's true that f of 2 is equal to f of 4. Negative 15 is equal to negative 15. So we are good on all 3 conditions. Thus, comma, there exists a c value that is a member of the open interval going from 2 to 4 such that the first derivative evaluated at that c value will equal 0. In other words, somewhere on the open interval we're going to find a tangent line that has a slope of 0. How do we find that point? How do we find that x coordinate? We take the first derivative of our function, f of x, which is equal to negative 12 plus 4x, and then we set that thing equal to 0. So 0 equals negative 12 plus 4x, solve, and we get an x value of 3. That x value of 3 is on the interval, therefore we can present that as one of our solutions. Is it possible that you're going to get thrown a question where the solution that comes up is not on the requested interval? Absolutely. And so for that question, you're going to have to say that there's no solution on that interval. All right, let's look at another question. From my homework set, this was number 6, and let me write down the question quickly for you. So this question wants us to find a c value that satisfies the mean value theorem given our function f of x equals the square root of x on the interval, closed interval, from 0 to 16. Thankfully, because we've made it this far in our study of mathematics, or if you are requested to go back and prove it, we do know that the square root function is continuous on the closed interval. So I'll jot down, well, f is continuous on the closed interval and differentiable on the open interval, 0 to 16. I know that it's differentiable because it's smooth and continuous. There are no asymptotes, no holes, nothing like an absolute value where there's a sharp corner. So it is going to be differentiable. And the slope from the beginning point to the ending point, so I'm writing m sub 0, 16. That's not necessarily standard notation to write it that way, but I'm able to explain to you what it is that I'm writing so I can get away with it, is equal to y2 minus y1 over x2 minus x1, which is equal to 4 minus 0 over 16 minus 0, which is equal to 4 over 16, which is equal to 1 over 4. So somewhere on the square root graph, on that curve, between x values of 0 and 16, there's a point such that the tangent line will have a slope of 1/4, which is a pretty low slope. Like it's relatively flat. I might even draw a little sketch. I don't know that you want to put this into your notes just yet, but it'll be on the screen for you to reference. So our square root graph looks a little bit like that, and if this is 16, and we need a point that has a tangent line with a slope of 1/4, it's almost flat. Maybe it's gonna, maybe an x coordinate like this one, that's freehand, but I don't know. So it looks like it's going to exist. It's possible anyway. So having met all of the conditions, let's go ahead and try to find the c value. Let's find c such that f prime of c is equal to 1 over 4. To do that, we're going to need to take the first derivative. So f prime of x is equal to, take the exponent of 1/2 from the square root function, multiply it down, keep the variable, decrease the exponent by 1, so 1/2 minus 1 becomes negative 1/2, and we want this to equal 1/4. So what I did is I went from exponential form back into radical form and wrote this as 1/2 times 1 over the square root of x, and that's equal to 1/4. And the left-hand side of this equation could be written as one fraction. 1 over 2 root x equals 1 over 4. If we raise both sides of this equation to the negative first power, we take the reciprocal of both sides of the equation. Divide both sides by 2, you get the square root of x equals 2, square both sides, and you find that x is equal to 4. 4 is on the interval from 0 to 16. Not drawn to scale, obviously, so the hand-drawn diagram was a little bit off, but it looks like there is a c value between 0 and 16 such that f prime of c equals the slope of the line that passes through the beginning and ending points of our interval. Also terrible. Don't use this diagram. Maybe you could trace a Desmos diagram or graph, or trace it off of your graphing calculator or something, because obviously the yellow line that I just drew is not parallel to the red line that I drew in this diagram, but they should be, and they should both have a slope of 1/4. All right, I'm not an artist. I'm happy to admit that. And I do have one other question that I thought we should look at. And this is from my homework set, is number 7. Let me just jot down some quick details of the problem. All right, so I've written down just sort of a summary of the details of the problem, and let me talk to you about this for a moment. What this problem is telling us is that we have a function such that the rate of change of the function, or the slope of the function, or the slope of the tangent lines on the entire function are between 2 and 3. So this it's rising, it's continuously getting larger because our slope is always positive, but it's not too large, between 2 and 3. And what we're trying to do is to find the maximum and minimum values of this expression. So we're working on this particular interval that goes from 2 to 6, because these are our x values, an x value of 2 and an x value of 6. And I know that the slope of the line between the starting and ending points of my graph can be calculated by taking essentially y2 minus y1 divided by x2 minus x1, and depending on what these y values end up being, f of 6 and f of 2, depending on what those y values end up being, that's going to change the slope that I'm calculating here. By the mean value theorem, the slope between the starting and ending point is going to impact the slope of tangent lines to the curve, and we know that the slope of the tangent line to the curve is always going to be somewhere between 2 and 3. Could be 2, could be 3, going to be between them though. So what I'm going to do is I'm going to set this equal to the slope of my function, f prime of x. And I'm also going to multiply both sides of this statement by 4, which is this denominator over here, so that I have, I just can't get my colors situated. All right, and what is it that we want to know? What we want to know is the minimum and maximum values of f of 6 minus f of 2. And the fact that this is the quantity that I'm looking at, or looking for, is what compelled me to multiply both sides of this equation by 4, so that the left-hand side of that equation matched up with what it is that I'm going to be working with. All right, well, can I use anything else that I've written down or any other given information to try to help me determine those maximum and minimum values? The answer is yes. I'd like to bring, well, we're going to be going back and utilizing this piece of information, which I meant to draw in red. There we go. We're going to go back and use that piece of information, and we're going to combine it with something else that we know. It's a constraint that was given to us that said that 2 is less than or equal to the rate of change of our function, which must be less than or equal to 3. And what I'm going to do here is multiply this entire compound inequality by 4. So we've got 4 times the 2 over here, and 4 times f prime of x in the middle is less than or equal to 4 times 3. 4 times f of prime of x, where does he get this stuff? Why would he want that? Well, it should look familiar to you. So I'm going to be going back and using that starred statement. And in fact, well, we'll go one more step before we utilize it. Let's make this an 8 is less than or equal to 12. Let's use it right now. I'm going to say by star, in other words, I'm going to use the information from my previously starred statement, which is up here, okay? By the information contained in that statement, I can replace, I can replace this with what 4 f prime of x is equal to, namely f of 6 minus f of 2. So let's do that. or we'll try to anyway. Here we go. Simple substitution. Unusual, probably, that the multiplication by 4 happened earlier, right? Multiplying both sides by 4. Why would I have thought to do that? It's going to take experience and exposure to more types of these problems, but being mindful of the resources that you've already seen, that was supposed to be a star, terrible, and while at the same time being mindful of what it is that you have as a destination is going to help you restructure earlier statements and turn them into something that's usable later. All right, that's a lot of scribble all over this page. Where are we going with this? I'm going right here. This format now matches up with this format, which means that the minimum value of f of 6 minus f of 2 is 8, and the maximum value is 12. Those are your two solutions. That is the end of my explanation of information from Chapter 4, Section 2. Thank you so much, and I'll see you in 4.3.